Today we're going to illustrate the use of mixture models for density estimation in the context of a real data set called the galaxies dataset. And what I want to do is I want to contrast mixture models fitted both from a Bayesian and a frequentist perspective against the density estimators that you get from KDE, from kernel density estimation. We're going to use the galaxies dataset. This is a very famous, well-known dataset used in the context of mixture models. And it's included in R as part of the mass package. You can do a help for the name of the package to obtain this information that is here. And you can see that these are velocities of galaxies measured in 6 well-separated conic sections of the corona borealis. So we want to understand whether this distribution is multimodal, how many modes are present, and in general provide a density estimator for these different velocities. Okay, so the first thing that we need to do is we need to actually load the data set. That's what this part of the code does. And we're going to be using 6 components in our density estimators using mixture models. The reason for that is that, as you can see here in the help file, there are 6 well-separated conic sections that were collected. So that suggests that there should be about 6 clusters in the data. Okay, so the first thing that we're going to do is we're going to use the EM algorithm to get the maximum likelihood estimators of the parameters for this particular data set. And once we plug those maximum likelihood estimators of the parameters into the definition of the mixture model, we can obtain what we can call the maximum likelihood density estimate. Based on the location mixture of models. That's very important. We're going to be using location mixture of models because they are the ones that compare more directly with the kernel density estimator. Okay, same structure as when we did the EM algorithm before. We need to provide initial guesses for the weights, the mean, and the standard deviation of the kernels. That's what it is. We need to initialize some parameters, basically that control the convergence of the algorithm. And then we go through the E step that has exactly the same form that we had before, and the M step that also looks the same as when we illustrated the algorithm for the first time. And actually, if you look carefully at the code, this is exactly the same code that we had before. Okay, so that's what this piece of the code does, and then we just compute the density estimator at different positions by computing the density evaluated in the MLEs that we have obtained after convergence. So this is very simple, and we can run this piece first, if you will. Okay, great. And you can see that it converges not as quickly as it was converging before when we did the simple simulated data. It took 44 iterations to converge, but it still converges relatively quickly. We pretty much didn't have to wait any time to get results. Now we want to do the same, but with a Bayesian equivalent of the model. So now we need some priors, and again, we're going to use the same priors that we used before. So the prior for the weights, it's going to be a uniform. That's why we use multiple ones. Here we have a little bit of a harder time setting prior distributions for the location of the kernels. And what we're going to do is we're going to do something that is a little bit like empirical Bayes, in the sense that we're going to roughly use the data to give us a sense of where they should be. And the estimate is going to be relatively robust to these choices as long as we keep them within one order of magnitude of this. So for the mean of the means, if you will, we're just going to use the average of the data. That's what this line does. And then for the variance of the means, we're going to use the variance of the data. That is essentially the choice. And then we also need to provide priors for the variance of the kernel. And in this case, I'm going to provide a prior that is an inverse gamma. The shape parameter is a 2, which means that it's a prior that doesn't have a lot of concentration. In fact, the variance of an inverse gamma prior with shape parameter 2 is infinite. So we're going to have a prior that has finite mean but infinite variance. And we're going to center it around the observed variance in the data divided by the number of components. Again, this is, roughly speaking, a reasonable order of magnitude. It doesn't change the results too much. Okay, so these are my prior specifications. So the rest is very similar to what we did in the past. So we're going to have some variables that store the posterior samples. In this case, we're going to use a total of 12,000 samples. We burn the first 2,000 and use the remaining 10,000 for inference. Then we run our algorithm. So that has the same structure as before. So we sample the indicators, we sample the weights, we sample the means, and we sample sigma. And finally, we compute the log posterior, the unnormalized log posterior, in case we want to check convergence of the algorithm. And once we have computed or sampled all the parameters, then we can compute the density for each iteration of the MCMC. That's what this piece of the code does. And we can even compute the posterior mean as a point estimator. So again, let's run the code. And again, it's not terribly slow, but it does take 10 or 15 seconds to complete the 12,000 iterations of the sampler. And then to compute the density estimators, but it's done now. So the last thing that I want to do is I want to plot the estimators and compare them against the kernel density estimate. So you can see here in the figure on the right are the results. Let's start with the kernel density estimator, that it's the red dotted curve. You can see that it agrees with the other curves down here in this little mode down here. It also agrees with the other ones down here. The main differences between the three are here. And what the kernel density estimator does is it tries to smooth out. It does see that there may be kind of two modes located here, but it kind of tries to smooth this out and make it look like a single mode. That is a little bit different from what, say, the EM algorithm, which is the dashed blue line, does. So again, it agrees with the other methods in kind of the tails of the distribution in these small clusters, but it is very different from the other ones, both in that it definitely picks two modes down here, very well delimited, if you see them. But it also differs down here in the sense that it doesn't really pick this extra mass or this extra weight that is down here that is due to these observations. It actually, the EM algorithm, the point estimator that it provides, gives very low probability to these values observed down here. In some sense, you can see the MCMC algorithm as being somewhere in between the other two methods in terms of what they provide down here in the middle. So it does show evidence of the multimodality, but it's not as strong as in the case of the EM algorithm. And on the other hand, when it comes to dealing with this little cluster of a couple of observations down here, it tends to provide more weight in that area than the EM algorithm was doing. So it's an interesting trade-off. But in any case, the results from all three methods are reasonably close, and they all show that there is definitely multimodality in the posterior.